perhaps want to give a very brief introduction of us as well?
Oh yeah, absolutely.
Yeah, very brief.
That's part of the presentation actually.
Okay. All right, cool. Then if that's the case, go ahead.
Yes. Yeah. All right. Yeah. So thank you again. Thank you for the opportunity to give this short introduction to TypeDB, and also how we envision TypeDB as a new programming paradigm for databases. And yeah, I wanted to start with a few words about who we are. So TypeDB, the company, London-based database technology company, and developing a database, also called TypeDB, which, to begin, is a general purpose database, but of course it's also strongly focused on other things, in particular on flexibility when working with diverse data, on safety, on modularity for developing complex applications, and performance as well. And the way we are approaching this problem is by trying to champion this new database programming paradigm, which we also refer to as the functional database programming paradigm, which this talk is going to be about. And besides that, there's a pretty mature ecosystem, so language drivers for a variety of languages, graphical user interface, and I'll get back to that at the end of the talk as well. So about us, TypeDB was founded by Heiko, by education a computer scientist, but also worked in robotics and optimization. I think this is where he developed the idea and saw the need for a modernized database, a new kind of high-level database, and he's the CEO at TypeDB. And myself, I actually have a background both in mathematics and computer science. I'm still an associate researcher at Oxford, working there on mathematics actually, but full-time working as the head of research here at TypeDB. So that means helping a bit to bridge the theory and the practice, and guiding, designing, helping develop TypeDB as a cutting-edge database. So TypeDB is a general purpose database, and there are a few innovations which I want to highlight. Of course, databases are a very mature topic, so we're not trying to reinvent the wheel entirely. There are lots of components in there which you'll recognize: query plan optimizer, execution and traversal engine, a storage layer, and so on. But the highlights, and it's bolded on the slide, is really the type system that governs all of these components, that interacts with all of these components. And then on the other hand, also the query language TypeQL, which is what the user uses to interact with TypeDB as a database. But I don't want to spend too much time on the engineering details today. So maybe the takeaway is just, it's a general purpose database with a type system at its heart. But besides that, it's a database with the usual bells and whistles. So ACID compliant, has encryption and security features, data replication, cloud as a service is something we offer. It's built for scalability and so on. I also wanted to address the question why we built TypeDB. Of course, there are many databases out there. First and foremost, that's relational databases. But by now, over the last decade or so, other database paradigms have also emerged. So there's document-like data and graph-like data. And the fact that these have become quite successful is really a reflection that data is very diverse. So there are many different data structures in the real world. And some databases nowadays approach this through multimodality. So they try to essentially encompass all of these data structures together. But often what that means in practice is that they pick corners. So they, let's say, start with a relational database, and then they bolt on these other features, document features and graph features on top of the relational database. So you end up with something that's more of a Frankenstein situation of a database. And that's precisely not what we were trying to do with TypeDB. So we wanted to think about data and data structures from first principles. And as many of you will probably agree, type system are a great foundational starting point for that, because it's really a foundational way of thinking about data and data structures and how they interact. So the type system that we built has a set of simple core types, a set of core kinds of types. And that's based on a distinction on two axes. So on one axis, we have the distinction of what terms, of what instances these types contain. So they either contain objects, which are abstract data points that, however, can interact with other data points through references. And then there's values, which are printable data, which can be used in other programming contexts as well, like strings, booleans, and so on. And the second axis distinguishes between independent and dependent types. So we're going to go into the details on that for sure. But what you end up with is this 2x2 matrix of types. So we're talking about entity types, relation types, and independent attribute types and attribute types. So that's the type system. And then what TypeQL does, or the role that we see for TypeQL, is really, in a way, allow access to that type system, but in an intuitive way. So it's really focused on being accessible also to users which are maybe not familiar with dependent types. It tries to package this type system using almost natural language-like syntax. And there's just a handful of keywords, of important keywords, and those actually closely correspond to the type system, and we'll explore that in this talk. So the one thing I want you to take away, though, is that if you think about data from this more fundamental approach, you do indeed get something that's more general than these other approaches. So in a way, this type system easily subsumes, it integrates relational data, document-like data, or graph-like data. So that's one of the key goals in this endeavor. So what are the use cases of a type system-based database? Well, first and foremost, it's what I just mentioned, the direct and intuitive modeling of diverse data. So you don't need to bolt on new data features. You can just define them, which I'm sure many functional programmers will identify with as being a great thing. But then the type system, of course, gives you more. Like it's based on simple core components, and that means that you often really simplify working with very complex applications because you have these clear and customizable guarantees from the type system that you can work with. So that allows you to make local changes to your program without breaking the entire application, even if it's a very complex system. And in that vein, we see the step from to TypeQL from SQL similar as, say, from JavaScript to TypeScript, or from C to C++ to Rust. There many other features. I'm really focusing only on core ideas here. So, for example, we're working on, or TypeDB, TypeQL is a polymorphic query language, meaning we allow users to work with type variables that allows them to write adaptive queries. That in particular simplifies use cases where you need to very dynamically work with your schema, where you want to migrate the schema and so on. And it's also meant to simplify your tech stack. So that's definitely one of the key use cases by cutting out intermediate layers like object relational mappers. And then there are a bunch of other features which we'll touch on briefly, like reasoning over data from this functional perspective. We are working currently on the next big release of TypeDB. It's overall a fast evolving database and ecosystem. So that's TypeDB 3.0, and this talk is already going to use some of the syntax from that upcoming version, which we are very excited about. Yeah, so to put it in maybe one phrase with TypeDB and TypeQL, we envision that we want databases to catch up with modern type programming languages. Okay, so that gives you a bit of an overview, gives you a bit of context. Now I wanted to get into more details, starting with the data model. So this part is going to be somewhat more theory-driven, and then in the next parts, we're going to see some practical examples of how you would interact with TypeDB through TypeQL. So as a fast overview, maybe you've noticed that already from the terminology that we've chosen for our types. There's definitely some structural similarities to conceptual and entity relation data modeling. And we do very much lean into that similarity because it helps our users onboard onto TypeDB. That's often what data scientists are familiar with, not so much type theory. But really, fundamentally, it's rooted in theoretical ideas and type theoretical ideas. Two key ideas. And the first one is subtyping, so the ability to cast between types. Maybe as a quick example, you could have a type of person that could have a subtype, let's say a type of adults. What that means is every instance of adult can be cast into a person. And on the left here on the slide, I'm showing mathematical notation, and then on the right, this is actually how you would declare these subtyping relations in TypeQL. So a single type can, of course, have multiple subtypes, and I wanted to also highlight the connection to some types here. Again, hopefully that will be appreciated by the functional programmers. So we have the special keyword abstract, and if we define the type as abstract, that means precisely that it's only the sum of its subtypes. So saying that person would be abstract in this example means that a person is either an adult or a child. So that turns subtyping into subtypes. So that's the first idea, subtyping. And then the second idea is type dependencies, which is maybe less common. But what it means is that you allow in typing a term, in forming a well-typed term, you must also provide a reference to another term. So just to spell this out, type dependency means that to type something, you require a reference to something else, to another object. And a good example from semantic data modeling here are names, because names usually name something. So you need to refer to whatever it is that owns the name. So in type notation, you would write n is a name of x, for example. In TypeQL, you would write it using a has statement. So that's the main keyword. You can, in some situations, also write that in different ways if you want to emphasize the variable n more than the variable x. So the name n must reference an owner in this context. So there's a dependency of the name type. But of course, conversely, in this setup, this type name of x can have many names in it. So a single x by default can have multiple names, unless you impose additional constraints on the type. So those would be precisely the cardinality constraints that Matthias was thinking about earlier. It also means more than that. It's in a way a causal dependency, and it also makes sense to impose that these dependencies are acyclic, so you can't have cyclic dependencies. It means that if you delete what's being referenced, then you also need to delete what's referencing. So if you delete the owner, then you also need to delete a name. So unless we're talking about independent attributes, which is less common, and I'm kind of omitting that from this talk, then a name always must have an owner. And again, to programmers, that can also be phrased in a more familiar way, namely we just avoid dangling references here. So this is an example of a type dependency for attributes. Then a similar story can be told for relations. So you can have a marriage M, for instance. So M is a marriage between X and Y. So that's also a form of type dependency, a dependent type, which has corresponding syntax in TypeQL. It's a different keyword, so it's not fully symmetric. It's aimed at being at expressing relations. And there's also a small asymmetry here that you always have one reference in ownership statement of the name, and you can have multiple references in relations. And that just makes the model a bit simpler. There's one more detail here I want to talk about, which is in order for this to be well typed, X itself must have a certain type. So for example, not everything has a name. Maybe a marriage usually doesn't have a name, right? So X must be of a certain type. That's usually how dependent types work as well. So it's a typed reference. And the way we make this work in our data model is by introducing what we call interface types, which describe the valid things you can reference. And for relation types, they're called role types. For attribute types, they're called ownership types. But let's also see an example here. So starting from the same type dependency, n is the name of x, what can x be? Well, this is an abstract type. It's the type of, let's call it the type of name owners. And the way this is declared in TypeQL is by telling the system what can be a name owner. So that's where the keyword owns comes in. So you would write person owns name to declare that things in the person type can be a name owner in particular. So as I mentioned, name ownership is an abstract type. So as a result of that, name owner then becomes a sum of whatever can be name owner. So for example, person or city could be name owner. So city can have a name, a person can have a name. And there's a similar story again for relations. There's a appropriate keyword for that. It's not owns, but it's place. But otherwise, the story is very similar for relations. Okay, there's one more thing I wanted to say about this high-level overview of the data model, and that it's unlike the other data models. If you really break down these other data models, it's very principled. It has these two ingredients of subtyping and type dependencies. That makes it very modular. So working with references and interfaces makes it very modular to describe what can depend on what. And it's generally flexible through the use of subtyping in representing all types of different data structures, sum types, subtypes, and so on. Yeah, and that's not really the case for other data models, but there's a translation that you can do to see how these data models integrate. Given some other talks about it, you can find them on the website. Yeah. Okay, so there was the theory of the model. Now I wanted to briefly look at an example and show you a bit of our data definition language. And I just wanted to start from a small data set. So this is a bunch of, let's call them data points. There are some abstract data points representing, for example, myself, and then a data point representing my name. So that would be a value, and so on. So in order to build a TypeDB schema, you would first categorize your data by types and by subtypes. So for example, maybe my colleague, me, and my boss are employees. But then you also have the opportunity to introduce subtypes. So for example, there could be a subtype of managers that specializes the type of employees. And yeah, you could do the same for the other data points. Let me first tell you how you would write precisely what we've just seen. So this sort of definition in TypeQL. So you would write define entity employee that introduces the employee type, and then you define entity manager sub-employee. So that's the data definition language to make this sort of schema structure work. Yeah, and then let me just fill in the other types. I will not go into too much detail. There's another entity type in pink on the left, a type of projects. Yellow denotes the relation types, and blue the attribute types, and various subtypings between those. But we're not done yet. We also need to think about how our data depends on other data. So for example, I mentioned that Christoph is my name. So it will be dependent on me. In particular, if I get deleted, probably Christoph, the name will be deleted too. So we want this to be well typed. So what we do is we introduce corresponding dependency. So we introduce that employees in particular can be the owners of first names. And again, how would you do that in TypeQL? You would write it using the owns keyword. We've seen it before. You would write define employee owns first name. Now it gets a bit more interesting because we also define manager sub-employee. So that was the definition that we made earlier. So in particular, this means that we now have well-typed statements in our language like the following. We can say M as a manager has first name Stephanie. So that's well-typed. Even though M is of type manager, it now can have a first name because managers can be cast into employees, and employees can be cast into first name owners. So of course, subtyping is transitive here. Similarly, this works for relations. So one of our data here are task assignments. So task assignments probably only make sense if they're assigned to someone. So there's an assignee of the task. And on the other hand, maybe you want to have a model in which tasks always have to have a project that they're associated to or that they live in. So you can introduce a dependency on a task on a project. So task assignment effectively acts as a relation then between me and the project in which the task is assigned. We want this to be well typed, so we do something similar. We introduce appropriate type dependencies through interfaces. So we say employees in particular can be the assignees of a task. So they implement that interface, they implement that role, they play that role of task assignees. And projects can be the projects of a task. In TypeQL, this uses the keyword place. So that's the complement to owns. So you would write employee place task assignee, and you would write project place task project to implement these interfaces. And this now means that the type system recognizes tasks can reference employees and projects in the queries that you run on the database. All right. One short addition to that is that, of course, you can have various forms of subtyping. You can also specialize these interface implementations as long as everything commutes. But it's a detail of the data model that I think goes a bit beyond the introduction. And it's also pretty straightforward. Okay, so we end up with a data model that looks like this. And the one thing I wanted to say about it is that, well, the first observation is that with simple ingredients, so just subtyping, which is this nesting of boxes in the picture, and dependencies, which are the arrows, you get pretty sophisticated data models. This one I would call probably still a simple model, but you can build very sophisticated data models with these two simple ingredients. And just to show you the full schema definition language, it would look something like this. So this defines the schema on the left. And if we would be going through it in more detail, you'd see that every component of this graphic on the left one-to-one corresponds to some declaration on the right in TypeQL. So for example, we've seen entity employee, the definition. We've seen manager sub employee as a definition. There's also a definition that defines the relation type task, which has the roles assignee and project. And then further down, we have employee owns first name. We've seen that, and place task assignee. So it implements those two interfaces. Okay, and I wanted to round things up with a brief comparison of how this data model at least compares to the relational data model. And to begin with, there's certainly no tables or columns anymore in the data model. They're just types. But you get more than that. You get through subtyping, you get inheritance hierarchies. So you can model how types organize in hierarchies. You also get something very interesting. So through interfaces, you can model in a way multi-table references. So references that can go to multiple tables at the same time. You can also, in a very modular way, connect tables and columns. So two different tables could point to the same column if you wanted to. So you have a lot of flexibility there. There's no need to explicitly manage foreign keys. There's no need to explicitly manage join tables if you want. All of these are part of the type system. They're implicit in the type system. And I also wanted to highlight that if you combine this with subtyping, join tables and subtyping, you actually get exponential decrease in complexity of your code. Otherwise, you have to consider a lot of permutations there. Okay, that was the definition language. The next thing I wanted to talk about is the data manipulation language. And a brief summary of the highlights. So I think the data manipulation language is really one of the most beautiful aspects of TypeQL. In a way, it's truly declarative. So SQL is often also called declarative language, but really, if you think about it, it's very operator-centric. It uses these relational algebraic operators, joins, unions, selections through where clauses, and that often forces you to transform your declarative query into something that's more procedural and works with these operators. The syntax, as you've seen in some of the examples already, is directly inspired by natural language. So we often prefer writing something that looks more like natural language than writing something that looks like heavy type theory, which we do believe simplifies the life of our developers a lot. And in fact, we've talked about ICFP earlier, but the language and the data model was formalized and published. It was published in ACM Sigmod Pods this year. So we've just were in Chile last month, actually, presenting the paper, and we're very excited that we also received an award. We received the Best Newcomer Award, and yeah, that was very cool. But there are many things which I think are truly innovative about TypeQL, type variables, which no other query languages really have. So in a way, this gives you parametric polymorphism. So you can write what we call parametric query, and so on. Okay, so that's some of the highlights. And then I wanted to look at two examples. The first one is data insertion. So here's roughly the same data set that we looked at before. So it's the data set together with all the dependencies. So I mean, I picked a very highly dependent data set for illustrative purposes. But yeah, so they're all the causal dependencies between that data, what depends on what. I've labeled them with links and has just to distinguish whether it's an attribute that depends on something else or whether it's a relation that depends on something else. I should also say the arrows point in the direction of the dependency. Semantically, it often makes more sense to think about the has in the opposite direction. So I have the name Christoph, but really the name Christoph will be deleted if I get deleted. So this is the direction of the dependency. So how would you write that in TypeQL? So this is what we call an insert clause, which inserts data into the database. I've ordered it by the different types that we have in our schema. So the first block here inserts employees, and at the same time actually also inserts attributes of those employees. So you would write insert me is an employee, has first name Christoph, call, I mean, abbreviating colleague, call is an employee, has first name Jean. My boss is a manager. And then similarly for projects, you would write P is a project, has name intro talk, P2 is a project, has name write docs. So these are the entities in our model. And then you could insert relations. One way to insert relations is without referring to them with a named variable. So you can omit the named variable simply by writing project P1 assignee call is a task. So that inserts a task for project P1 with assignee call. But you can also use a named variable to represent that relation object. So you could write insert task 2 is a task, links project P2 assignee me to now have this variable as a named variable to further work with in your insert clause if you wanted. So for example, you could then go ahead and insert a review, which says review is a review, has score 0.3, links task 2 reviewer boss, for example. So again, there's a very close correspondence between how you would think about this at a visual level and how the language is designed. Yeah. Okay. Second use case, of course, would be data retrieval. For me, that's always the most exciting part to talk about. So we do data retrieval with a match clause. And on this slide, I just wanted to contrast data retrieval in TypeQL with maybe how you would describe it in natural language and also how you would do it in SQL. So in TypeQL, data retrieval is through a match clause. You would write, for example, match B is an employee, has name Mark, R is a review, links reviewer B, task T, has score S. T, so the task T, links assignee E, project P. P has start date greater than the beginning of this year. E has name contains Jean. And that would be an example of a match clause. So that's already pretty close to how we would naturally talk about the query. But just to illustrate that, let me also go through the natural language counterpart. So you would write maybe, find me an employee B who has name Mark. Find me a review R of some task T reviewed by B, and retrieve the given score S. The task T should belong to some project P that has start date later than the beginning of the year. And T should be assigned to an employee E whose name contains the substring John. For 10 seconds, I'm just going to say that in SQL, you're forced to reformulate this query in a more operator-centric way. And you might also have to write some subqueries. By the way, I was too lazy to do the syntax highlighting for SQL here. So it was not meant to be an unfair advantage, but you do have to rewrite the query substantially in that join an operator-centric way. But yeah, so there's actually this other clause select down here. And to understand what that does, we do need to talk about what match outputs and how you can consume it. So match, well, intuitively, it finds all the answers to the declared pattern. And what's an answer? Well, an answer is an assignment of all of these variables to either objects or values or types. So it can be multiple things. But what you can do then is you can use further clauses. So select is one of the further clauses. You can also use a fetch clause to do a transformation into a JSON object. But you can use further clauses to operate on the stream. So it's really also functionally inspired. It's like an iterator that you can map on and then filter on and then do more things on. Or you could even, in TypeDB 3.0, you can even chain a match with something else and then another match to like extend your answer further with new results. So it's this functional way of thinking. You get a stream in and you can further operate on it. And yes, the thing you get for R is an object. So it's an abstract data point. But then further down the line in your pipeline, you can do more things with it. You could use a fetch clause to output a JSON, and in that JSON, you can retrieve attributes of that object. So you can further manipulate that object and turn it into readable values in the fetch clause, for example.
Basically, to simplify the three possible answers, basically select returns a map of concepts. And in your driver, that's literally in Java, it would literally be an actual Java hash map where the key would be the name of the variable and the map value, the entry value will be an actual object to the concept. And so that concept could literally be a type or a thing or an attribute. And so it's like an actual programmatic object in the language of your driver. So that's option one. Option two, you can, instead of saying select, you can say fetch. And so from R, you can say fetch all the names of R, all the attributes of R. And so with fetch, it basically projects that concept into a JSON map. So that's just a straight up JSON object that will contain a map of the keys will be the labels of the variables, and the get content of that JSON object will be the attributes that you fetch. The third option is to literally in TypeQL, not returning yet not returning the answers yet in your driver, but in TypeQL, you can chain match with another match or with an insert, with a delete, or well, in this fetch is actually part of that chaining of that stream. So we have the native representation of treating it as a map in TypeQL itself and continue chaining the queries before even returning it.
Okay, so maybe some key takeaways with match, with TypeQL's match, you can do a lot in a single pattern. So you don't have these operators, joins, unions, and selections through where. The principle that enables this is something that we call queries as types. So this this union of data retrieval and types and conditions on them, that's really one big type, one big data structure that you're constructing. And well, types are compositional in a way, so these patterns are also compositional. You can just take two patterns, glue them together, and that would be another valid pattern. And then there's the second aspect, which we just expanded on a little bit, which is that we have these functional pipelines of streams of answers that we can operate on. So match returns a stream, and then you can do more things. You get another stream, and so on. And maybe you want to then have a terminal operator, a terminal thing that turns this into some other output. But you have this functional perspective, this compositional perspective on how to build your queries. The optimization happens in the background, so the user doesn't need to worry about it. And I think it's also noteworthy that all of create, read, update, delete fits into the same syntactic approach. So the example didn't show this, but you can also use the data definition statements in your query to retrieve type objects if you want, and then work with those type objects. All right, a brief word about the ecosystem. I'm gonna keep it very brief though, and also the future, the plans that we have. One thing that we're really excited about, also in the context of TypeDB 3.0, is extension to our reasoning engine. TypeDB 2.x already has a very powerful reasoning engine. It's more closely inspired to how Datalog works. It's a mixture of propositional and type theoretic thinking, if you want. But with 3.0, we really want to embrace the functional database paradigm. So instead of writing propositional rules, which especially for complex application can get a bit cumbersome, you have the option to define functions, use those functions in a recursive way as well, and build essentially a reasoning system over your data with those functions. And well, functions are typed, they are named, so that makes it much more intuitive and also more scalable in terms of maintaining your code when working with them. Then there's TypeDB Studio, so that's our graphical user interface, which has a lot of features when it comes to schema manipulation. So it's quite easy to manipulate the schema inside TypeDB Studio using the interface, but also running queries, retrieving results, graphically representing results are features of TypeDB Studio. All right, so the future, I mentioned it, I think at least 3 or 4 times, but we really want to work out and embrace this functional database programming paradigm. TypeDB 3.0 is a major step towards that goal. It's a rewrite in Rust. It has a lot of streamlined syntax, some of which you already saw. It has this generalization of what we previously called rules to functions. And one of my personal things that I'm very excited about is also rewrites of drivers. Going to come with 3.0 of language drivers, because I think we will really try to exploit this flexibility in data structures to tailor, for the first time, tailor the database to the programming languages rather than always tailoring the programming languages to the database. Yeah. There are many other directions that we're exploring. We're thinking on the side about retrieval augmented generation. I think there's a good foothold there for TypeDB because of the proximity of TypeDB and natural language. I think that'd be something really interesting to explore. But yeah, there are a couple of future projects on the horizon that we're thinking about at the moment. There's also a TypeDB roadmap. That's something you can read about on our blog, and some more in-depth articles that are linked from that blog post. So if you're curious, you can find that on our website.